this is the quick talk, quantum information and coherence talk. This is supposed to be at the tutorial level. So people who are joining it, the students who are joining it for the first time, this is supposed to be a tutorial level talk that should make you get interested in this broad field of quantum information and coherence. So, well, I'm very happy to have Professor Ebrahim Karimi today from University of Ottawa giving this talk. In fact, he's giving a series of talks, 3 talks on Monday, Wednesday, and Friday, same time, 5 to 6 India time. For him, it's 7:30 a.m., but he is still fine at giving a talk this morning, that morning. Okay, so just a brief intro about Professor Karimi. So he has a BS in physics in 2001 from University of Kerman in Iran, and an MS physics in 2003 from Institute of Advanced Studies, same university in Iran. 2009, he has a PhD from University of Naples in Italy, and currently he is a Canada Research Chair Professor at University of Ottawa. So he has several research accomplishments, there's too many of them, but his research is mostly focused on structured quantum waves and their application in quantum information. So you have several papers, about 150 or so in all major journals, including Science, Nature, Nature Physics, Nature Photonics, PRL, you just name it. He has also 3 patents. He's a member of the Royal Society of Canada and Global Young Academy. He is also a fellow of the Optical Society of America. He is a visiting fellow of Max Planck Institute of Science of Light. And he's also a fellow of several other societies. He has several prizes as well. The few that I can note is this Ontario Ministry Early Researcher Award in 2018, University of Ottawa Early Researcher in 2019, and Canadian Association of Physicists Herzberg Medal in 2020. He was the Associate Journal of Physics until 2020, and he's currently the Associate Editor of Express since. One thing I'd also like to say that he actually started his physics journey with theoretical science, theoretical physics, mostly string theory actually. And then from there, he actually shifted to quantum optics experiment. So I think it should be, his talk should be, to people who are students who are interested in theory, as well as, of course, everybody working in the quantum optics experiment. So with that, let me hand over to you, Professor Karimi.
So thank you very much, and for first of all for inviting me. I think there is an important point that I should say and add to this, which is that Anand and I, we can be somehow science brothers, because we both have the same, we had same supervisor, which is Bob Boyd. And usually we have these jokes in science community that we look for grand supervisor and etc. So we link each other, because we know very well that the mentality, the colony of thinking is coming usually from the supervisor. So thank you very much, Aaron, for giving me this opportunity to talk to your, let's say, students or members of your institute. I think this is the second time that I'm giving talks to IIT. When I was a master student, there were a couple of opportunities to visit there, because as you say that I was a theoretician actually at that time. And I know that in India, we have so many great theoreticians, and India and Iran, they are common in this sense that they are really, most of physicists, they like to work in string theory and high energy physics. While there are a lot of things to be explored in applied optics or applied physics. So, and the other things that I want to just say that this morning, the Optical Society or the OSA has changed name, and now is Optica Publishing Groups. So it's completely new name. So it just happens about maybe 5-6 hours ago. Anyway, so I will start with, since this is going to be a tutorial, I need your feedback, and any places that you don't feel that you feel that you are not following properly, or there are something a mystery there, just hold me back, and then we will have a discussion about that. Okay. So, and by the way, should I be restricted to 1 hour, or can we go to, let's say, 1 hour and 15 or 1 hour and 10 minutes? Anand?
Up to you, perfectly fine.
Okay, beautiful. So let's me start with sharing the screen and share the screen. It is, the talk has been arranged in such a way that first, I will give you a short, let's say, overview of what I mean by structured quantum waves. And today's talk will be really basics. And then next talk, which will be on Monday, will be about the applications, essentially quantum communication. So let's say some satisfying your curiosity. And then the quantum communication and quantum simulations with structured waves. And on Friday, the talk will be completely different. It will be about a new field of research, which with my colleague in 2010, 2012, we found and we started to share results with other colleagues. So let me start with this way that I said, as I said to you, that today and tomorrow and on Monday talk will be about the structured photons, which we will discuss about that manipulation, generation, manipulation, and detection of them. And then high dimensional QKD with structured photons, a survey of different QKD protocols and channels. However, before going there, let me briefly, let's say in about 10-15 minutes, telling you a lot of fun stories that we know about the structural light. So today and on Monday will be about photons, and on Friday will be about electrons. Okay, so structural light. The first thing that when someone tells you a new topic is that you will copy paste it, you'll place it on Google, and you Google it, okay? And what you receive is that. So if you check it out, you will get structural light. The first thing, the good point is that you will find something like a Wikipedia page about that. And you love that because it seems that someone put a lot of efforts to introduce a new topic to you. You check it out and you realize that the structural light here means that having a device, a quick device, an accurate device, which works like a 3D scanner. So it sends a lot of laser to trace, I don't know, face or an object, and then from the reflections, they will understand that what is the shape of the object. This is the definition of structural light. Okay, good. And this is not what I'm going to talk about. So don't Google it, please, okay? What I will talk about is more broad, and it starts from a fundamental question. And the question is that we know that light is electromagnetic waves, and you will see it, let's say, on the second part of the today's talk, that when we start and deal with Maxwell equation. And the question is that, does light carry mechanical effects? Okay, so any thoughts, guys? I would like to be interactive one. So no answer? So does light carry mechanical effects?
Anybody wants to speak, just unmute and you can just speak.
Yeah, exactly.
Sir, is it radiation pressure?
Very good.
Light carries momentum.
Beautiful. Okay, let's see. So, and I think both of you are right. And we know that, for example, from sci-fi movies in Star Trek, they had a spaceship, which the spaceship worked based on a solar cell. I mean, they call it solar cell, okay? So what happens? So the light, as you say, that carries momentum, linear momentum. The momentum is coming in, and this is a reflective object. So the object without absorbing light, it will reflect it. And when it reflects, then what is happening, we do have a change of momentum. And the change of momentum will move the spaceship in space, okay? I think I heard this year also they had some spaceship like that, which is working based on, let's say, radiation pressure of the light. Good. And you can do a little bit of mathematics. You understand that that is related to the energy of the light and then the angle that the light is reflected. Beautiful. And know that this is not new. Almost is almost about 300 to 350 years that we know about these phenomena that light carries linear momentum. So if you look at comets, if you look at several comets, what you will see, usually you do have two tails. One of them is always away from the sun, okay? So it's opposite direction of the sun. And the other one is look like some dust, which is with the gravitational, let's say, effects of the comet is following the comet, and then in a certain point when you don't have a kinetic momentum, it disappears. And the one that I'm talking about, and I like it very much, is the blue one, which is always directed away from the sun. This is an ionic tail and is always, let's say, against the sun. And what is happening, this is due to the radiation pressure that they will get it from the sun, okay? So we know now very well that light has linear momentum. And this will be affecting the particles. Even in such scenario, you will observe it in the macroscopic scale. And this was formulated by Poynting, and that's fantastic. So it's just one form of wave. Now the other question is that, can we make an object spin with light, guys? Any thoughts? You can unmute and just tell me.
Orbital angular momentum.
Yes, orbital angular momentum. Anyone else? I'm talking about spin. Rotating.
Circular polarization.
Circular polarization. Okay, beautiful. Let's go and see what else we can do that. So we know that the light has a linear momentum, okay? It's like the air flow. So if you assume it is the radiation pressure that you will get it. If you want to spin an object, what you will do? You can design the object in such a way that it will be spin, right? So something like a pinwheel. So you can create a device or create an object which is look like a pinwheel. But then when it receives the radiation pressure, the momentum is such a way that you have let's say, a transverse momentum, and this transverse momentum will cause your rotation. And indeed, yes, this is a design. You can create an object which is created by one of my colleagues in Romania, and this is a let's say, micro scale. So it's a size of, let's say, smaller than my hair. And it looks like a pinwheel. And if you see that the symmetry here is broken, and when the symmetry is broken, then when the radiation pressure is coming here, you will get a transverse momentum transferred to that object, and the object starts to rotate, okay? And indeed, this is a movie of the experiment. So assuming that you have such an object trapped in a liquid, and then with light you can make it spin, and and the scale is about, let's say, few micrometers. And this is wonderful. Now let me ask a question which Professor Anand also answered, is that, oh, okay, fine, assuming that my object is symmetric, so the object that I do and I design is not the symmetry is not broken. So now we know that the pinwheel is not let's say, left-handed is right-handed, then the rotation will be in opposite direction. But now assume that I have an object, which is, this object is symmetric, is look like, let's say, a circle, like that, okay? Can I rotate it?
If we can vary the type of light that's hitting it, like the intensity as its distance from the center, we could make it get orbital momentum.
If the intensity or something else, or the phase? Okay.
Like if the distribution of photons can be affected, in that case we can make it rotate, even if it's a symmetric object.
Okay, so let's see if that scenario works. I will come back to your idea later on when I'm talking about orbital momentum. Let's do that. So, well, let's do a little bit of mathematics, okay? It's a tricky question. So when we say spin or rotation, we have to be a little bit careful. So first of all, light, as we discussed, we know that it carries linear momentum. Fantastic. So what is the linear momentum? 1 divided by 2 mu naught E cross B, and this is the pointing vector, right? Associated to the pointing vector 1, divided by C, of course. And if an object carries linear momentum, then we know that if you define a coordinate, then you can calculate what is going on with angular momentum, okay? So let's say like like baseball, for example. You have an object is coming to you, and then you try to kick the ball, and then the distance that you do have it from the ball will define what is going on with angular momentum that you will have, and you will introduce to the object, and then that will be the trajectory that you will have it. So essentially, the distance will define the value of orbital momentum, let's say angular momentum. So J, which is angular momentum density, is defined by R cross the pointing vector or linear momentum with a coefficient. And then you can, what you can do a little bit of mathematics, essentially. Let me see if I can write anything here. So this is what I mean. So you know that the light carries linear momentum. Now the point is that if it carries linear momentum, you can define a coordinate, which this coordinate is R. Then you say that, okay, R cross P is my angular momentum, J. However, remember that these angular momentum density, so at the end, what you have to do, you have to integrate on the 3R, okay? So if you take J and you do the integration, you will get the total angular momentum. So I know that I know Maxwell equations. So B essentially for a monochromatic waves, we know that the curl of E, which is given by minus time derivative of B. So by the way, are you familiar with Maxwell equations, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so if anyone doesn't, so just tell me, give me a heads up, so I will try to explain it a different way. And then for a monochromatic wave, we know that B and E, they are proportional by e power of minus I omega t. So if you replace it here, what you will get an expression for B, which is given by minus I divided by omega curl of E. So for a monochromatic wave in a free space, I can replace it here, then I will get this equation. So now I have 3 cross products. So R cross E star cross curl of E. So you can expand this, and when you do the expansion, you will get 2 terms, and you integrate it, of course, based on the fact that total angular momentum is given by integral of J over the entire of the space. So expanding this, it will give you two terms. The first term is given like that, and the second term is given by that. So essentially, J, the total angular momentum, now is split out in two parts, which is S and L, and each component of them, I and J or K, so it's given by this expression. So is integral of entire the space is E star J, E K, and you have an operator intermediate, which is the Levi-Chita operator. And the other side also, what you have E star J, E J, and then you have an operator here as well. So let me ask a question. So can you tell me what is your feeling about these two equations? What is evidence from these expressions? And explicitly from these. Anyone? And don't afraid, just don't be shy, just tell me.
They are some kind of angular momentum operators.
This one, right?
Yeah.
This is look like R cross P in the quantum mechanical language, which P is replaced by I, let's say, in unit of H bar, of course, nabla. Do you agree?
Yes.
Yeah. What about this one? Anyone?
Looks like some cross product also.
Levi-Chita, like a cross product?
Yeah, yeah.
Okay. What is evidence? This is a tensor, right? Do you agree? Do you know what is tensor, of course? Roshi? I think I heard it. Yeah.
It's a tensorial product. It might relate to the polarization or the intensity.
Okay. So you are all right. Okay. So this is a form of orbital angular momentum, and this is a form of spin angular momentum. Look, there is no sign of coordinate here. Okay, so there is absolutely nothing related to R here. So like, I don't know, rho, phi, theta, whatever. So this is independent of the coordinate, while that one is look like the form of a kinetic momentum, okay, or kinetic angular momentum. So this is what we call them spin angular momentum, which is independent of coordinate, and that is angular momentum, orbital angular momentum. And electric field sounds like that these look like a wave function. It looks like psi star, psi here. Of course, remember that there is an ik here. For that one is more explicit. It looks like psi star. So essentially, even this is, we start with completely classical picture, which is Maxwell equation. But what we found for the spin and orbital angular momentum, there are two operators which they are one of them is independent of the coordinate and the other one is depending on the coordinate. Okay, so we call that one spin term and the other one orbital angular momentum term. Is that clear? Good. So now I'm interested in the spin, let's say in angular momentum, if my beam is propagating in a specific direction and I choose the coordinate such a way that the coordinate z direction is along the propagation direction of my beam, or let's say the electromagnetic wave. So we have a radiation pressure, and then I assume that the coordinate has been chosen such a way that the z is along the propagation direction. Then what I'm interested in is finding Jz. So if you know that J has T component, Jx, Jy, and Jz in that coordinate, and what I'm interested in is Jz, finding out what is going on with the longitudinal component of angular momentum. So Jz definitely, based on the calculation that I have done, has spin z plus Lz. Okay, so it has two components. One is spin angular momentum and the other one is orbital angular momentum. And let's do a little bit of mathematics and finding out what is going on with each term individually. So if you do the calculation, so you are fixing I now with Z. Now I, you fix it with Z. So here is Z, and I know that only two components of these epsilon I, j, k will not be zero. One of them is this one, x, y, and the other one will be y, z, y, x. And then if you expand them, what you will get that S, z essentially, or these epsilon I, j, k, if you write in form of, let's say, a specific basis, you will get exactly the sigma z of Pauli, okay? And for the other one, if you look at only z component, in the cylindrical coordinate, if you look at the r cross nabla and the z component of that in the cylindrical coordinate, you will get something like derivative with respect to phi. Is that clear, guys? Any questions? No? Okay, I assume it's fine. Then, if I write it in the circular polarization basis, which we will be discussing about that later on, so assume that this is just a specific base, then I will get this expression, which is very interesting. So one of them is left-handed circular polarization, the amount of photons in left-handed circular polarization, minus the other handedness of circular polarization, which is right-handed. Okay, so is number of photon in left-handed minus number of photon in right-handed. This is the classical one, by the way, the expression that I have written here. And that one, the derivative with respect to phi will appear on the left-handed and right-handed circular polarization. So now I am asking a question, guys. So I have a photon, which is a quanta of light, and this photon is circular, let's say left-handed circular polarization. So what is the spin angular momentum for this photon? I have only one photon. So one single photon, it is left-handed. Exactly, it is exactly h bar. So if it's left-handed, then spin angular momentum of that will be h bar. If it's right-handed, what it will be the value?
It will be minus h bar.
Minus h bar. If I have three photons, which they are all left-handed, then it will be 3h bar, right? So then I can say that in the quantum regime, a single photon carries h bar of angular momentum along propagation direction if it carries either spin, let's say a left-handed spin angular momentum or right-handed spin angular momentum, okay? So if it's left-handed or right-handed, the value essentially will be given by h bar per photon. So now let me ask another question. Are you familiar with plane wave, right? I think this is the first thing that someone will solve it in a course, an electromagnetic course. Plane wave is given by exponential of I, K, Z, Z, if it's propagating along Z direction. So can you tell me if the plane wave carries angular momentum? We are not talking about polarization because polarization is different. And now we are talking about the spatial structure, which is this term. Oh, let me rephrase my question in a different way. When this term will not be zero, Anyone?
It's plane wave.
It is what? Plane wave. If I have a plane wave, do the derivative with respect to phi will survive? Because for plane wave is exponential of ikz, right? There is no dependency on phi. It is only on z. No thoughts? When electric field, either left or right, they are the function of phi. When they are function of phi, then the derivative with respect to phi may survive, and then you will get the results. So let's give an example. When f of phi is harmonics, so is I m phi, then the derivative with respect to phi will be I m exactly e power of I m phi. Then you will see that the LZ component will appear. So the important point is that, so in order to get angular momentum or orbital angular momentum, you need to have an expression which is function of phi, okay? And we will see in the next slide. So we will review that. So we have the electromagnetic waves, and electromagnetic waves carries linear momentum. So upon propagation, it interacts with an object, it can move, push it out. And on the other side, we know that also it carries angular momentum. One of them is related to the vectorial nature of the light, which is showing how the electric field tip is rotating in space and time. And this is carrying only 1 unit of h bar per photon. Either will be plus h bar or minus h bar. We will talk about that again. And the other form is orbital angular momentum. When the LZ operator, which is derivative with respect to phi, will give you a value. Let's say you look at the expectation value, and for specific wave function or electric field, you will get a result, which the result is not vanishing. So a simple example that I gave it to you is that when the electric field has a dependency, which is given by e power of IL phi. So assuming that you have as in the previous case, this is the Z, this is X and Y, and now you assume that your electric field in such a way that upon a full rotation, okay, which is changing phi from, let's say, a value of phi 0, if you do a full rotation and coming back to the same place, so it will be 2 pi rotation plus phi 0, then you will get exactly the same physical results. So that is what I have written here. So L should be an integer. L is an integer quantity, okay? And we know that the wave also is propagating in time and space. So it's given by this expression. So this is a plane wave. So assuming that you have the propagating wave, as soon as you have this functionality, e power of IL phi, independent of being left-handed or right-handed, it carries angular momentum of LH bar, which is different scenario from the previous case. The previous case was spin angular momentum, and it only can take 2 values of plus and minus h bar, and that was dictated not by the phase of the beam, but was dictated by being left-handed or right-handed superposition. So that was related to vectorial nature. Here, no, this is related to the phase nature of the beam, okay? And there is another difference. Here is bonded in the case of polarization, superposition left-handed or right-handed. Here is almost unbounded. It's given by any integer value of angular of h bar, and this is amazing. So as I said, that L is integer, and you can create those sort of things in the laboratory. We will just review a little bit of these today. So and some people, they may ask me, how, okay, fine, I know that electromagnetic waves has a vector, has a phase, but can you tell me what is the structure of this beam upon propagation? So if it looks like that, usually if it's propagating in the z direction, usually we are familiar with the planar wave. So it's, these are the constant phase place. So either these phase of 0, this is 2 pi, this is 3 pi, sorry, 4 pi, and etc. So for a plane wave, essentially the constant phase or co-phase are in plane. This is the reason we call it the planar wave. However, when you have an angular momentum, so the phase dependency shows up as azimuthal dependent in the phase. And if you plot them together, for example, for the case of L equal to 1, then the phase is not anymore planar like this one, but the phase becomes spiral. So this is the co-phase region. So essentially all of those points that they are in this surface of helix, they have exactly the same phase value. And for these sort of beams, you have an angular momentum of plus h bar. You can have a negative L value, so it can be -1. So then what is happening, the handedness will switch, okay? And when the handedness switch, then you have negative value of angular momentum, which is minus h bar. Then you can have L equal to 2, and then what you have, you do have 2 points which they are in the, let's say in a transverse plane, you have 2 points which exactly they are co-phase, and they are going like a DNA structure essentially. And in a high order, essentially you can have let's say L equal to 3 or -3, and then you have 3 points in a transverse plane. For in each transverse plane, you have 3 points which they are all a co-phase. Clear, guys? If you have questions, just let me know.
Oh, okay. This is very nice. Just one quick question. So if you could just go one slide back.
Sure.
Yeah. So this ERZ that you have. So does that play any role in deciding how much orbital angular momentum one has? I guess the Allen et al., they showed it for Laguerre-Gaussian mode. So that means the E has some specific form. So does the form of E matter as far as, you know, this LH bar assignment is concerned, or is it just completely independent? All you need to have is just e to the IL5 over there.
So you can just put e power of IL5 here. You can just add it here. And if I understood your question, is that this expression is depends on this value of L or not, right? Was that the question?
No. So let's say IL5 is there. So now my question is, this ERZ that you have before e to the IL5, does
Yes.
that decide what is the orbital angular momentum one is going to have? Or is it,
no,
as long as you have e to the IL5, the moment angular momentum is decided?
Exactly. So the point is that all is dictated by these phi, derivative with respect to phi, okay? So I assume that now if you look at the previous example that we had, we say that, look, hey guys, sorry, I think I went quick. So the important point is that here, right, the derivative with respect to phi of ER and EL, they should not vanish, okay? So it means that only phi functionality is important for us. As soon as we have an electric field, which is given by f of phi, times whatever you have it for R and Z, okay? This is playing role for getting orbital angular momentum, okay? So I mean, if I want to rephrase myself again and explicitly answer into your question is that no, this is not important at all for getting the OM value. However, remember that when you put L here, you have some restrictions on this value, okay? Because they should satisfy, let's say, Maxwell equations.
Okay.
Okay. So we will give few examples of that. Yes, go ahead, please.
Yeah, so in that 92 paper that Alan, they did, so they showed this specific calculation for Laguerre-Gaussian mode, that if you integrate over enough volume that the energy density gives you h bar omega, the same volume will give you LH bar for the orbital angular momentum. So, so that result was, I mean, that derivation was specifically for the Laguerre-Gaussian mode, but you're saying you will have the exact same derivation no matter what is the form of ERZ.
Exactly.
Okay.
Exactly.
All right.
I will give you an example of that. So, for example, for many people, many years, many people, they say that, hey, guys, we are creating Laguerre-Gaussian mode. No, many people, they didn't know that they are not creating Laguerre-Gaussian modes. They were creating a different type of mode, which I call hypergeometric Gaussian. So, which is the ERZ is completely different form. It's not necessary that ERZ will be a unique one. You have freedoms of that. But as I say, that L will dictate somehow what is the E component, okay? And you have some freedom there, but not totally, let's say, independent. Yeah, but in answer to your question, yes, explicitly, this ERZ has nothing to do with orbital angular momentum.
Okay, all right, thank you.
Fantastic, absolutely. Any questions?
So I have another question regarding on the same line. So we heard except that Laguerre-Gauss, also we heard about Bessel-Gauss and Innes-Gauss beam. So they also carries e to the power IL5 phase. So does it can be useful for generating OM modes? Means they can be also used for OM modes, is it?
Yeah, exactly. So all of those beams that you mentioned, Suman, if I pronounce your name correctly,
yes,
all of those, yeah, fantastic. All of those beams, they have this term, as you pointed out. All of them, they have e power of IL5. What is E R Z? Okay,
yes.
They are different, and they are different depending on the coordinate that you solve the problem. It can be Laguerre polynomial, okay, multiplied by Gaussian. By the way, first of all, if it should carry finite energy, it should be Gaussian term. So definitely it has e power of, oops, sorry. Okay, definitely it should, when it's e power of IL5 and this is ERZ, if you want to have a finite energy in space, definitely that is given by E minus rho squared. Some other term as well, which is E again of, not E, let's go something else. Let's go with E of R and Z. So you have an additional term here. So this term, it can be Laguerre polynomial, it can be Bessel, it can be Mathieu, or it can be whatever function that you want, hypergeometric. So it depends on really what you are looking for. So how many solutions do you have? So many solutions, I cannot count it. When you find the proper physics for it, people, they will buy the idea, okay? Did I answer to your question, Suman?
Yes, thank you.
Beautiful. Okay, so now just to remember, guys, that we...
Sorry to interrupt. Can I have one more question, please?
Absolutely, Ruchi.
Yeah. So for a beam to carry orbital angular momentum, does it necessary to have exponential IL5 or a beam without this term? So, but
it should have this term. If
But-
it doesn't have e power of L phi, no, it doesn't carry orbital angular momentum.
No, but then if there is a spatial distribution such that it is having a phi dependence but not coming through the phase, through amplitude, so then also can a beam carry or OAM?
Look, it can, look, for example, if we go to the pinwheel, okay, this carries, I mean, due to the symmetry broken of the object, you can carry angular momentum, or you can imprint angular momentum to an object. But this doesn't mean that your beam is carrying orbital angular momentum, okay? You can have a specific distribution. As far as I know, in order to have a specific distribution, you cannot do that without shaping the phase. So you have to play with phase. And when you do play with phase, then the phase should be helical form. With intensity, you cannot do that.
Okay. But
Yeah,
I
for
have
example,
seen some papers like they've mentioned about the elliptic Gaussian beams. They do carry orbital angular momentum without having any optical vortices or any OAM.
can you write the expression for me in the meantime?
Expression, I do not have the expression, but I can have some papers. Like it's OAM of a Gaussian beam. Or I'll just type it in the chat box.
Yeah, beautiful. Send it to me. For example, I can tell you something that you can have 3 beams, okay, coming at angles. All of them, they are Gaussian, or let's say plane wave, and then they carry angular momentum.
Yeah, yes.
But they have to come at angle, and this angle means that you are controlling the phase.
Yes, absolutely correct.
Yeah. So if you let's say look at the general expression for the beam, if they are coming at angle, let's say 3 angles like that, one is coming here, and the z component is like that, and then one beam is coming here, and the other beam is coming from the other angle, then you have to look at the projections of all of them, because the coordinate that you define is these, and then you will see that definitely this term will appear there. Okay, not necessarily that it is a single quantum, maybe it is a superposition of different L values.
That will be actually multiple beam interference you're trying to refer. Like you are generating lattice structures, right?
Beautiful. So send it to me, the paper. Do you have my email? I think you should have it. Send it to me. I will look at that. It's all, I would say that based on simple calculation, if you decompose it, or if you have a proper representation, definitely it carries orbital momentum. Okay?
Oh, sure. Yeah, thank you.
Fantastic. Absolutely. So now let's go back to the mathematics. So the vector, how the vector of electric field is oscillating in time and space. If it's going left-handed and right-handed, they will give you spin angular momentum per photon, which is quanta. The quanta is h bar. If the phase is structured such a way that you have e power of IL phi, then the phase structure will become helical, and then you have orbital angular momentum. They are different, as we showed, I mean, based on the expression that we had. So now the question will be, okay, I know that the phase is like that, and the phase becomes helical. What is going on with intensity profile of that? So let's give you an example. So the phase is changing from 0 to 2 pi, right? Right here. What is happening for this explicit case is that the phase, this is the constant phase value. And if you look at the transverse phase, so this is the z direction, this is x and y. Now what I do, I don't look at the along propagation direction, but I look at the transverse plane. And the transverse plane, if you remember, it has a phase which is given by e power of IL phi. All right? So it means that here, for example, for the case of L equal to 0, everything is constant phase. So this is the 0 phase. For the case of L equal to 1, here is the, let's say, 0 phase. Then it becomes pi divided by 2. Here it becomes pi, and here becomes 3 pi divided by 2. Now going to the center, reduce the radius. This radius has this structure of phase. Going to the center, this radius has exactly the same phase structure. Here is 0, here is pi divided by 2, here is pi, here is 3 pi divided by 2. What about the origin, guys? What is the phase at the origin? At r equal to 0 or rho
It can have
equal
any
to,
phase actually.
pardon?
It can have any phase from 0 to 2 pi.
It can have any phase. And or should I use another word for it? Should I say the phase is undefined, as one of our colleagues says, or the phase is singular? Do you agree on that? It looks like going to the North Pole, right? So going to the North Pole, each of us, we have a time zone. For example, India right now, it should be something about maybe 6 something. In Ottawa is about, the time is about close to 8:30. And when we go to the North Pole together, just one step before the North Pole, we do have the time defined, but when you go to the North Pole, the time is undefined. So here, the same scenario, phase is undefined. When the phase is undefined, we call those points singular phase. And this is the original idea. We call that this research field, before knowing the orbital momentum, we call it phase singularity. And I think Remarkably was among the first people that he called that phase dislocation. Okay. Beautiful. And then Marczewski and other colleagues, they work extensively in this field, and they expanded the field in many different aspects, and people, they understand what's going on with singular optics. Okay. So when the phase is undefined, then I'm expecting that there will be no intensity there. So if I look at the intensity profile at the origin, it's at the transverse plane, I see that at the origin there is no intensity. This is the reason that all of the beams that they carry e power of IL phi or orbital angular momentum, they have no intensity at the origin. This one is a plane or Gaussian wave, which essentially it doesn't have the e power of IL phi, then you don't have that. And just going back to Ruchi's question, so if you want to have a phase singularity, essentially, if you want to carry orbital momentum somewhere, you should have e power of IL phi, okay? And when you have e power of IL phi, it means that in a certain point, you should have a phase singularity, and in a certain point, you should have a null intensity, okay? Let me be a little bit careful and tell you that the phase singularity is much broader than orbital angular momentum. Phase singularity can happen in any places in the transverse plane, while in order to carry orbital momentum, these phase singularities should be exactly at the origin, okay, or along the beam axis propagation. So when the phase singularity is along the beam axis, then we call this orbital momentum, or we can say the beam carries orbital momentum. But however, we can have a beam which has multiple phase singularities, but it does not carry orbital momentum at all. Okay? In general, locally might carry, but in general doesn't. So we have to be very careful with the word of orbital momentum. A good example of that, as I previously was shown, is pasta fusilli. Anyway, and these also when you visit Ottawa in a park which is at front of Parliament, of Canada, you do have this helical structure there as well. So I'm trying with my hand just to show you that this is the direction of, let's say this is the K vector of the beam. Good. Now, someone may ask you, good, fine. I know that now what is the spin angular momentum, which is related to vector property of light, what is the orbital momentum, which is related to the phase structure of the beam, but what is going on with the Poynting vector? Remember that the Poynting vector is not spiral. This does not look like what is written in papers. I mean, Anand knows very well because he's working in this field. If you look at the literature review, you will find out that they say that the beam is twisting. Absolutely, this is not the case. Assuming that you have a bunch of pencil and you twist them together. Each of them, they are a straight line. But if you look at them, they have a transverse, let's say, component of that. And this is the property of orbital angular momentum. You are not expecting that you do have a spiral K vector. What you have a straight line of a K vector, but each of them, they are twisted. And this is shown for the case of orbital momentum of 2, that how this is propagating. This is shown a beam that is focused, and after the focus, you will see that each point is going to, let's say, from different clocks to a different clock. So how there is a huge difference between spin and orbital momentum. As I said, it started from the question that I raised and asked you. And this is the difference is given by interacting with material. So when you have an object, or let's say an electromagnetic wave, which carries spin angular momentum, and you are interacting with a material, spin will cause the object to rotate around its own axis. While orbital angular momentum, it forces the object to rotate around the beam axis. And these are the two experiments done by my colleagues. In the right figure, let's say left figure, what is happening? I have a beam which carries orbital and spin angular momentum, which is causing the rotation of these micro-sized sphere to rotate counterclockwise, and this one is going clockwise side. So you have two beams. One of them is left-handed, the other one is right-handed, and with this you can create a pump. And here, instead, what we have a non-trapped micro-sized particle, which I'm shining a beam that carries orbital momentum to it. And what you will see that those micro-sized particles, they start to rotate around the beam axis. So there is a huge difference, not only in this mathematical expression, and being one related to the vectorial nature and the other one related to the phase nature, but also in the way that they interact with small particles. One is causing a rotation about the beam axis, and the other one rotation around the particle axis. How do we create them in the laboratory? With superposition, it is easy. We can use a quarter wave plate or wave plates essentially to manipulate the polarization of the light. We can learn it. We can change it from linear polarization to superposition. Yes.
Yeah. One question. So, can you go back to the video that I was showing? That was pretty nice. Yeah. So in the right one, where we have the orbital angular momentum. So now I guess these tiny particles that you have, that the size of these tiny particles are much smaller than the size of the beam that is falling onto them, right? So now
absolutely necessary.
Yeah. So now if the particle is not in the center, are the individual particles seeing the orbital angular momentum of the original beam, or Or is it that they are seeing something different? I mean, in the center, they see it exactly same as the incoming beam, or when they are out in the periphery, they see some other number, but they make a circular motion around the center.
Yeah, so very good point. Indeed, first of all, you pointed out correctly, the size of the particle should be smaller than the beam. Okay, this is necessary to see these, let's say, mechanical effect. The other thing is that, so here, if you look at the case of orbital momentum, what is the intensity profile, as we discussed, is a donut shape, right? And those are the trapped particles. So they will be trapped in the places then you do have intensities. So they will be trapped here. Okay?
Mm-hmm.
And then what they see, essentially, you can have both expressions that you mentioned. Either you can go with a quantum mechanical picture and say that they will see the total angular momentum or orbital angular momentum of the beam, or you can do the mathematics and you will see that they can see the mechanical, let's say, property of the beam, and both of them, they are right. However, they have done these experiments also with atoms, okay, and they have seen that the atoms, they will pick up the let's say the quanta of orbital momentum, which is let's say the single photon angular momentum values.
Oh, actually,
there will be no atom at the origin, because this is not a place that you can trap the particle or the atoms.
Okay, so I was getting at the single photon, single atom level. So you're saying if I have a beam with some LH bar per photon, 3H bar per photon, for example, then it doesn't matter where the atom is in the radial direction, irrespective of its location in the radial direction, it will see 3H bar. I mean, it will get a 3H bar per photon. Okay, all right.
Exactly. And there is a beautiful work that they show that you can have intrinsic property of orbital angular momentum, mm-hmm. which is independent of where the atom is located.
Has somebody shown this experimentally? I mean,
yes.
Okay.
They have done that. Yeah, they have done that. It's a PRL paper, essentially, way back in early 2000, I think. So that the independent, where if you don't change the coordinate, which means that this origin is fixed, it doesn't matter where is the atom is located, it carries exactly the same amount of orbital momentum.
Okay.
It sees exactly the same amount of orbital momentum.
Okay, I look for and I'll ask you for reference if I don't find it. Okay, all right.
Absolutely. They call it intrinsic and extrinsic property of orbital momentum.
I see. Okay.
Yeah, exactly. Yeah. Thank you.
Thank you.
Yeah. How can we create them? For the spin is very easy. You can use quarter wave plates or wave plates in general to shape the polarization of light. So you can go from actually any linear polarization to, let's say, any arbitrary polarization. It should be defined polarization, because it can change also the state. Any polarization to any polarization by using a quarter wave plate, a half wave plate, and a quarter wave plate. So you can do, because the group that you have it is SU2 group, and essentially with these three rotations, you can map any states to any states there. And for phase, which is generating orbital momentum, it's a little bit tricky. What we need to do, we have to change the phase front of the beam to change from what we get it usually, which is a planar one, Gaussian, to become a helical one. So in order to control the phase, we know that the approach is usually given by, let's say, if I have a material like a piece of glass, I go with a planar wave, And then when I go inside of the glass, then due to having a different phase and group velocity, maybe what I will get, I will introduce a delay. So essentially, essentially if this is the phase that I have it, and after the propagation, this will be the phase inside of the object. So inside of the object, you have a different group and phase velocity. So essentially, if you look at the phase, you will see that it's shifted. So what you can do, we can use this approach to shape the phase front of the beam. So I can have a material which the thickness is function of phi. This is what I'm looking for. And this look like a spiral. Essentially, you will see that here is a low thickness, and in the other side is higher thickness, okay? And when the beam is entering, here exits earlier and here exits later. So then you will imprint a phase structure. However, the jump that you do have it in the thickness, it should be dictated by the refractive index and the value, wavelength of the light, and the value of orbital momentum that you want to imprint to the beam. And this is given by this expression. So in order to have L value of 1, let's say, then the thickness change, it should be in order of the wavelength. So wavelength that usually we work in the visible is 500 nanometer. So then the phase, let's say the step jump that we have should be in order of, let's say, assuming the refractive index, it should be in order of 500 nanometers. So then you should make that like a step functions, like a staircase. Then this is the first stair, and that's the second stair, and the fourth one, fifth one, and etc. So each step that you do have it should be in order of, let's say, fraction of 500 nanometers. So that's the reason that it was difficult from the beginning to create a visible light which carries orbital momentum. People, what they have done, they did it with a microwave. So they went to a much longer wavelength. I think I will stop here. But there are other ways, which is the holographic approach, which people, they can create orbital momentum as well. So what time is it right now? I think is 10 minutes is past the time, right?
Yeah, that is correct.
Should I stop here?
Fine, that is fine. Okay, so I think we have asked so many questions, but are there other questions that anybody would like to ask? Just unmute yourself.
Yeah, hi, Professor Karimi. This is Harsha. I enjoyed the talk. Fantastic. Thank you so much. I just wanted to talk about the video that you showed. So, for example, the situation where you have L equal to 1, and let's say you are right or left circularly polarized, then would you generate something that is not moving overall? For example, I could have my,
These are two beams, two different beams.
Okay. No, I'm talking about the stuff on the right. Let's say I also have the spin angular momentum here on the right, which could be, let's say, negating the orbital part. Then what is the structure that I see here?
Very good.
Will I see anything? Will I see this?
Very good question.
Will I see the circular formation of the pattern itself? Yeah.
Yeah. So spin angular momentum will be shown by the red motion. Okay. So if you have an object here, okay, spin angular momentum will cause a rotation around the object axis.
Correct.
Orbital momentum is shown with blue. What it does, it rotates around the beam axis.
Correct.
So the motion that you are expecting, it will be look like the motion of the Earth around the sun. So the Earth is rotating around itself. This is the spin angular momentum, as rotating around the sun, which is the orbital momentum motion.
Yeah, but if I look at the beam as such, as a whole, it carries, for example, zero angular momentum, because
Yes.
L could be, S could be plus h bar, and this is minus h bar, and then even then you will get that structure. That's interesting.
Yeah, remember the nature are different. One of them is rotating around the particle axis. The other one is rotating around the beam axis. You are totally right. The total J is 0. Okay, but
Yes.
one of them is causing a rotation around the beam, around the particle axis. The other one is causing the rotation around the beam axis.
No, my confusion comes from the fact that if you talk of a photon, as we imagine, which is a particle of some size, one doesn't distinguish between its center or a distribution.
Yeah, I understand exactly your point.
Of the field around it, or we just have a notion of a, and that is the confusion, where when you begin with something like J equal to 0, does it still create this structure at the single photon level? Indeed, at the more bulky level, I would agree with you. But at the single photon level, let us say, does this picture of defining a center, then going around it, or intrinsically, are these distinguishable at all? Is the worry. Sorry, I hope I'm...
No, you're thinking very fundamental, and I like it. Let me tell you something. Photon is not localized. Okay, this is the first thing that we should understand.
Okay.
The photon is a quantum object, and a quantum object is not localized. Prior to interaction with atom, prior to interaction with an object, you don't know where is the photon. Okay, so this is the state essentially that you do have it. Okay. So, but you know that the probability distribution to find photons is dictated by these, let's say, donut shape. Okay. As an individual, the single photon carries linear momentum, angular momentum, spin angular momentum. Spin angular momentum is completely independent of the coordinate. When it interacts with let's say with a particle which is here, or a particle here or here, what it causes, it's a rotation around the particle axis. This is the property of the spin. When it comes to orbital momentum, depending where is the particle is located, it gives a kick, which the kick it will be angular direction. So this is really the situation.
Mm-hmm. Yeah.
What I would say that we have to be very careful is that when we are doing this transition from classical to quantum world, and we want to compare it, we have to be very careful that also photon, as we usually assume as a quantum entity, is not localized. It is a wave. It is a wave.
Yeah. Thank you.
Of course, Abhinandan, right?
Yeah, Abhinandan.
Yeah. Yes. I have a question regarding this phase singularity picture that you have shown in your slide.
Hang on, I have a question right on the slide. Can I ask first, please?
Okay.
Sure. Yeah, this one.
So just continuing on Harsha's question. So if the particle that you were showing in the video, yeah. Sorry, now we are at this slide. Abhinandan, go with your question now. I'll come back next.
Okay, so you said that if this beam carries a definite angular momentum, then it will have a phase singularity, and that's why you're not getting any intensity. So now if my beam carries like a bunch of angular momentum, and if I add them incoherently, then still it has a distribution of angular momentum, but its intensity will look like a flat intensity beam. In that case, what will happen to like this phase singularity, or how can I think about this?
So when you talk about incoherent beam, means that you have to sum up all intensities together. Okay?
Yes, yes, yes.
So it will be like that. So it will be, for example, incoherent superposition of beam carries orbital momentum of -3, -2, -1, and 0. Okay, are you happy with
yes.
that?
Yes, yes, yes.
Let's do that. So if you do this, it will be the sum of these 4 intensities. Okay. you will see that the intensity profile, if I'm plotting in the row like that, its intensity profile will be like that. Okay.
Yes.
Okay. So
Yes.
this is the scenario.
And if I just add them like in a coherent manner, and then this, so there in this case, this phase singularity or the minimum intensity may not appear at the center. It may appear somewhere else, right? When I have a bunch of OM mode.
Yeah, if you add them coherently together, which will be the subject of next next Monday, next Wednesday, you will see that you will have a different pattern. So, for example, if you add them all together, depending on the relative phase. Now, the relative phase plays role as well. So it depends on how do you add them. So if it's you are adding, let's say, e power of I t phi with my negative plus e power of I minus 2 phi plus e power of minus I phi and etc. So it depends on what you put as a coefficient here. Okay. Then essentially you may get something like the intensity that is look like only this pattern, for example, something like that with the two lobes here or something different. Okay.
Okay.
We will discuss about that next lecture.
Okay. Thanks.
Sure, absolutely. Nilesh,
Yeah.
or should we go to Anand because Anand reserved the place?
No, Nilesh, you can go first.
Thank you. So I wanted to ask, so it's related to the slide itself. So as the orbital angular momentum increases from L equals to 0 to 3, we see that because of the phase singularity, the zero intensity spot increases in size. So I was wondering why. So is it because, say for L equals to 2, we have phi equals to 0 twice, and as we increase L, that 0 point increases, and we have sort of more difficulty in identifying the phase?
No, you are totally right. I cheated on this. I use a specific beam to plot. Okay, this is shown with Mathematica. So I explicitly consider Lagrangian modes, and when you use Lagrangian modes, essentially you have an expression for the amplitude. With the expression for amplitude also depends on L. As soon as you change L, also that is changing. Okay.
Okay.
In principle, if I don't have, let's say, a beam that is not a beam that is a solution to partial wave equation, as soon as you increase L, right? As soon as you increase L, the size of the ring will increase. How it increases depends on the amplitude. For example, for Lagrangian beam, the rate or the speed will be different, which goes with one of them is square root of L, the other one is L, the radius that the intensity is located, maximum intensity is located. But for example, you can have, let's say, a beam which is not a solution to partial wave equation. You have e power of I k z z minus omega t, and then you immediately place e power of I alpha. If you just want to show that, it will be a point in a mathematical point there as a phase singularity, and the intensity only at that point will be 0, and the rest no.
Okay, so it sort of, so to sum up, so it depends on the amplitude, and that depends on the sort of beam we are working with.
Exactly, it depends on the amplitude or the beam that you are working with.
Thank you.
Absolutely.
Okay, Pratik, you can go next.
Yeah, so we know that for to interact with atom and photon, so there there is a selection rule to obey, basically. So
Yes.
for this selection rule, the atom momentum is need to be matched with this photon momentum, basically. So in that case, this photon spin angular photon momentum, is it coming from the spin angular momentum or this orbital angular momentum or this total angular momentum?
Pratik, you raise a very important point and important question which I don't know the answer. Okay, let me tell. It might be, sound like that is an easy question. Okay. Well, the other way is easy. So you can have an atom, you can excite it. Depending on the level that you get a transition, and the transition, it can be dipole. When it's dipole, you have the Zeeman transitions, which you can create superposition left or right. That's not a big deal. People, they have done that. Even this is the basic for doing laser cooling. So people, they use the Zeeman transition again, going with beams that carry different spin angular momentum, different left-handed and right-handed, then you will cool an object, okay? And applying a magnetic field such as is that clear to you?
Yes. Okay.
Yeah, what about orbital angular momentum is more difficult, I would say. First of all, from the transition, yes, you can excite it, you can have a quadrupole transition, and from the quadrupole transition, you will get a photon which carries orbital angular momentum, which is higher than what you expect there, is not h bar and minus h bar. Remember that, however, the quadrupole transition is much lower than the dipole transition. That's the first scenario.
Right.
Let's go with opposite way. Let's watch it in the opposite way. Assuming that I have an atom, it goes back to a question that Harsha he asked. So
Yes.
my apologies for not pronouncing your name properly. So he asked, and this is also an important, and I think the two questions, they have a common phase. Assuming that I have a photon which carries only orbital angular momentum, and now I'm interacting with an atom. What is happening? First of all, the first thing is that remember that the size of atom is angstrom, and the size of your beam is usually, if you want to go with specific transition, is about, let's say, a fraction of micron. So there is a mismatch. So the beam size
If it is not a photon beam, then it is true.
If it's not,
if it is not a single photon, then it's true. But otherwise, the size,
even single photon, there is nothing mystery about the single photon, apart from the statistic. Okay, the statistic is a different scenario. And when you go to the photon pairs or other things, the scenario will be different. Whatever we have it for single photon is coming from Maxwell equations. So it look like assuming a laser beam, but now you are assuming a single photon there, okay? Or the thermal beam, which you assume only a single photon there, with the being coherent or incoherent, whatever. So even a single photon that you do have it is not localized, it's almost everywhere. Okay, is dictated by the beam size, which is the minimum size that it can get is given by Rayleigh criteria, which is about, let's say, 1 micron of the wavelength essentially. So for this specific case, is about the micron size, and the size of atom is angstrom. Now, if your atom coherence time is not, let's say, atom coherency is not so huge, and the atom is localized, essentially, atom will see just, let's say, the total angular momentum to be projected on specific state, which does not carry orbital momentum, okay?
Right.
The atom should see the entire the beam in order to see the orbital momentum, okay? How this can happen? By cooling down the atom, such a way that the Debray wavelength of the atom is comparable let's say, spatial distribution of the photon. In that case, you might have the orbital momentum transferred to the atom and you will get an excitation there. Apart from this, no, it is not possible.
Yeah.
You raise a very difficult question for me. So far, I don't know any experiment showing that. It's coupled to the transition, internal transition of atom.
Okay. Yeah, when you are describing the orbital angular momentum and spin angular momentum, I was just connecting that time. I think the spin angular momentum, the atom observe the spin angular momentum and make the transition. I mean, from your what you are saying.
Exactly.
But, yeah, I thought. Yeah.
Exactly.
I'm not sure about the.
When it comes to interaction with the quantum system, we can get a bunch of atoms and causing them to rotate. But so far, I have not seen any experiment. There is one experiment in Nature Communication 2000, maybe 16, 17, but that's a different scenario. It's a very difficult one. But apart from that experiment, I have never seen any work showing that orbital momentum of photon is coupled to internal degrees of freedom of atom.
Right. Okay. Thanks a lot.
Absolutely. Pleasure.
Right. Any other question? Well, I can go back. So I think you have kind of answered. So this is again going back to the video. So I was just kind of mostly commenting that if in that video, if that particle is in the center, then it will not see the orbital angular momentum of the incoming beam. I mean, I'm talking about the video that you showed.
Yes, I'm going there just to see if we do have this one.
The next one, yeah, exactly. Huh? So if the particle is the particle's axis is aligned with the beam axis, then no OM will get imparted to the particle?
Yeah, because there's no light there. Because it's a point of singularity, right?
Well, particle has some finite size and the singularity is only at r equal to 0. So let's say it is centered at the center, but it has a finite size. So in that case, will it still see, but it is in the center, in that sense, it is symmetric. It is not at any, r position. So will it
as soon as it's at the center, it will not see the OM. If it's displaced even by a very small radius, yes, it sees the orbital momentum.
Okay. All right.
Yeah, absolutely.
Okay, any other question?
Pratik is...
No, I think his hand was just not lowered, but I think. Okay. Pratik, do you have any other question? I guess he's fine. Okay, so this was very.
Yeah.
Yeah, you have one more question, Pratik?
No.
Fine. Okay. Fine. All right. So this was very nice and exciting. And again, we are looking forward to more on Wednesday. So the next lecture will be Wednesday, 22nd, same time, 5 p.m. for us. And for Ebrahim, it will be again 7:30 a.m. in the morning.
Anand, you wanted to change the time, right?
It looks like
for
we are
next because of the student.
Requesting him. He has already something on his calendar at that time.
Oh, I see. Okay.
So for Wednesday, I'm totally fine. But for
the Wednesday.
For Wednesday, I'm totally fine. If you want to shift it for Friday, no.
Oh, excellent. Okay, fine then. Then we'll do Wednesday at 6 p.m. Our own India time, and then for Ebrahim, it will be 8:30 a.m.
8:30 a.m. Okay, beautiful. 8:30 is fantastic for me. I'm sorry it went a little bit slow. Maybe Anand, if it's okay, I will only concentrate on photon this week, and whenever you want about electron, we can schedule another meeting.
Fantastic. That would be excellent. That would be excellent. Yes.
I like the discussion, guys. I mean, it reminds me of some fundamental question which I had it myself in the past. So that's the reason that I'm going a little bit slow. So on Wednesday, we will review quickly what is going on, and then we will go with application of it. And next Friday, it will be very extensive in terms of research activities.
Okay, excellent. All right, so let me thank you on behalf of everybody. Other we would have clapped, but that can't do on Zoom. So let me thank you on behalf of everyone. So thank you so much.
Thank you very much.
We'll see you on Wednesday. Okay.
On Wednesday at 8:30 in my time. Okay.
Yes. Okay.
Thank you. Bye bye.
Bye bye.